I don't know. Guess that's a new thing. It's going to start making that weird noise every time I turn it on. All right. So we are looking today at identities. Okay. There are a couple of trig identities that you already know, called them identities yet, but when we look at them, they should look familiar. What an identity is, excuse me, is just any equation that is true no matter what the value of the variable is. Okay, so for instance, okay, back in algebra, you learned factoring. Okay, if I have two perfect squares, okay, and one is being subtracted from the other, remember this is called a difference of two squares, right? And it factors into two binomials. Okay, the square root of the first term, which would be x, square root of the second term, which would be y, and you get 1 plus and 1 minus. Okay, that means that this equation should be true no matter what x and y are. This should always be true. That makes it an identity. Okay, so an equation that's always true, the left equals the right, no matter what value of the variable you plug in. Does that make sense? Okay, so we're going to test this out, make sure we understand how we test to see if something is indeed an identity or what makes it an identity. Okay, so if I were to look at the left side of this equation, x squared minus y squared, and the right side, x plus y times x minus y, and I were to pick any random values of x and y and plug them in, what should the left and right always come out? How should they always compare to each other? If it is indeed an identity. Okay, what makes an equation is the equal sign, right? The left side needs to equal the right side. So they need to equal each other. They need to come out the same if it's an identity. So in this table, you can see they have a column for x, a column for y, okay, and then a column for the left side of the equation and for the right side of the equation. Those should always come out equal. Okay, the left should equal the right. So we're going to take a minute. I'm going to do one with you, and then you're going to have some time to try some on your own. But you can see they have an example already worked out where they said, what if x is -3 and y is 2? So if you think about that, -3 squared is 9, 2 squared is 4, 9 minus 4 is 5. -3 plus 2 is -1. -3 minus 2 is -5. -1 times -5 is +5. Those come out equal, didn't they? So you're going to pick any random x and y values. So if I picked 5 and 4, for instance, I said, what if x is 5 and y is 4? And I go to plug those in. 5 squared is 25. 4 squared is 16. 25 minus 16 is what? Okay, so then I'm going to check this side. 5 plus 4 is 9. 5 minus 4 is 1. 9 times 1 is, there it is. So that one checked out. So I'm going to give you a minute to try one of your own. Okay, so take a minute, try one of your own. If you're watching this on a video, you can pause and try it on your own and then unpause, okay, and see a couple more worked out. Okay, so somebody just share what values you tried for X and Y. 6 and what? 6 and 7. Okay, and then we'll check the other one. Okay, so if I plugged in a 6 squared would be 36. And 7 squared would be 49. 36 minus 49 is what? Negative 13. Okay, if I plug in a 6 and a 7 here, 6 plus 7, that's 13. 6 minus 7 is negative 1. 13 times negative 1, we get the negative 13. So it checks out. Okay, and what was the other one somebody shouted out? 6 and 3. Okay, if I try the 6 squared is still 36. 3 squared is 9. So 36 minus 9 is? Okay, if I choose 6 and 3 here, 6 plus 3 is 9. 6 minus 3 is 3. 9 times 3 is also 27. So you can see that's the gist of what an identity is. That's what we want you to understand is it's an equation where no matter what value you pick for the variable, it's always valid. The left equals the right. Does that make sense what an identity is? Okay, now we've been dealing with trig for months now. We actually learned a couple of trig identities at the beginning of our trig unit back, I don't know when we started, October-ish. Okay, we didn't call them identities, but we talked about them, and these should look familiar to you. Okay, these are your we talked about them being reciprocals. We just didn't use the word identity. Okay, but the reciprocal trig functions, okay, you should know. So sine's reciprocal is cosecant. So sine of an angle is equivalent to 1 over cosecant of that same angle. So how could I write cosecant of theta equals 1 over sine of theta? Okay, cosine and secant are reciprocal trig functions. So if cosine is 1 over secant, secant is 1 over cosine. Tangent and cotangent are reciprocals. So you know these 6 reciprocal IDs. We have talked about them. We just didn't use the word identity until now. Everybody's familiar with the reciprocals, right? Okay. Now, the other one that you are familiar with, we just didn't call it a quotient ID, are these two. There's two. There's tangent and cotangent. What does the word quotient mean? What mathematical operation did you do to get a quotient? Okay, so tangent as division or a ratio of two other trig functions. What is it? Sine over cosine. Very good. See, you knew it. You know sine over cosine is tangent. We just hadn't called it a quotient identity before, but that's what it is. Because no matter what theta is, if we do sine of theta divided by cosine of theta, it will be equivalent to tangent of theta. Does that make sense? What would cotangent of theta's quotient identity be? Yeah, it's the reciprocal of tangent, so it would be the reciprocal of this ratio, which would put cosine in the numerator and sine in the denominator. Okay, so reciprocal and quotient IDs, those are familiar to you. Now you have a name for them. Okay, what we're going to discover today is what's called the Pythagorean identities. Okay, I'm going to go ahead and flip over to the back. They're called the Pythagorean identities because they are derived from Pythagorean theorem. Okay, so we're going to go ahead and flip your page over. Okay, and we're going to look at this graphic here. This should look familiar. We are used to drawing angles within a quadrant, right? And creating a triangle out of them to that point on the circle. Yes? Okay. So XY is a point on a circle. What part of this image is the radius of the circle? C, right? The radius is from the center to the edge of the circle. So C is the radius, okay, if XY is a point on the circle. Okay, it's centered at the origin. Okay, we're going to come up with 3 equations using this image here. Okay, 3 equations in terms of A, B, and C. Okay, the first one, part A, asks us to use Pythagorean theorem to write the relationship between A, B, and C. Well, this is a right triangle, isn't it? And A and B are the legs. C is the hypotenuse. So what could you write? Yeah, A squared plus B squared equals C squared. That is Pythagorean theorem. Pythagorean theorem says that the sum of the legs squared is equal to the hypotenuse squared, right? Okay, now B and C ask for ratios in this picture for cosine of theta and sine of theta. So I put an arc here where theta is. So do y'all remember your ratios for sine, cosine, and tangent? How do you remember them? Okay, so if you need to jot that down, SOHCAHTOA. That's a memory trick, so you can remember sine, cosine, and tangent ratios. What do the O, the H, and the A stand for? Yeah, opposite, adjacent, and hypotenuse. If you need to label that in your picture, you can. What is adjacent to theta? What's the adjacent leg? A, right here. Adjacent means next to. What's the opposite leg? Okay, and then the hypotenuse, we said, would be C. That's the radius of the circle. So if you need to label that to help you come up with these ratios, you can. But in terms of A, B, and C, little a, little b, little c, what's the cosine of theta ratio? Yeah, because it is adjacent over hypotenuse. So that is A over C. Okay, what about sine? Yeah, it's opposite over hypotenuse. So that's B over C. So in terms of A, B, and C, we have 3 identities here. Okay, we have 3 equations, okay, that we're going to use to do part D here. Part D says use substitution and simplification. We're going to combine those 3 equations into a single equation that is only in terms of theta. Okay, so only in terms of theta. So I want to be able to substitute for the A, and I don't want A and B there, right? So to do substitution, this was one of the skills that you were practicing in that Delta Math Algebra Skills Review, was substitution. If I want to substitute something for A, I need to solve this in terms of A, right? I need to get it as A equals. How could I do that? How could I get rid of divided by C? Okay, so if I multiply by C, it'll reduce over here. But what I do to one side, I have to do to the other, right? So A is equivalent to C times cosine of theta. Okay, now what about with B? I want to be able to substitute something in for B. So I want to solve this for B. What would I do? Yeah, same thing. I would multiply by C to get B isolated. So B is C times sine of theta. So now I'm going to substitute B with C sine of theta, and I'm going to substitute A with C cosine of theta. Okay, so I'm going to write that out over here. I have C times cosine of theta. Now that's still squared, isn't it? Because of Pythagorean theorem that A is squared. So that whole thing is squared plus, I'm going to substitute for B and square that, and it's still going to be equal to C squared. I haven't substituted anything for C squared, just for A and B. So that's C times sine of theta. Are we with me so far on the substitution? Now I'm going to do some simplifying. When you square something that is multiple terms, there's multiple terms in here. There's C and there's cosine theta. Both of them get squared, right? So that's going to become C squared times cosine squared of theta. And this is going to become C squared times sine squared of theta. Now there's still something I can do to simplify this. What do all of those terms on the left and right have in common? Yeah, they all have a C squared. So I can simplify by dividing that out. If I divide out the C squared, that reduces to a 1 in all of those instances, right? Now, I don't have to write it in front of cosine squared and sine squared, but over here, that's the only thing left. I do need to put a 1. So that ends up being cosine squared of theta plus sine squared of theta equals 1. So now I used Pythagorean theorem and my trig ratios, and I did substitution and simplification, and that's only in terms of theta now, right? The only variable here is theta. Okay, this is one of your Pythagorean identities. It's the most common one that you're going to use. Now, what's the sum? If I'm finding the sum, I'm adding numbers. Does it matter what order I add in? If I add 1 plus 2 or 2 plus 1, does that matter? No. So it doesn't matter if it's cosine squared plus sine squared or sine squared plus cosine squared, right? You're typically going to see it with sine squared written in front, but it's the same thing. Okay, so here in number 4, we're going to take that identity that we just found in 3D, okay, and we're going to do the same thing we did on the front. We're going to check in a table, okay? Our only variable is theta, and we want to check theta. We want to check an angle from all 4 quadrants. So somebody give me from one of the unit circle angles that we have the trig values memorized, okay, give me a quadrant 1 angle. Okay, so 45 degrees. Somebody give me a quadrant 2 angle. Okay. Quadrant 3. 2 what? Not 215. 220 is one. Yeah, we can do 220. Okay, what else for quadrant 4? Say again. 330. Okay. All right, so I'm going to test each of these angles and see, is this true? So this is just breaking it down for us to show our work. That's why there's extra columns here. But really, what should this equal in the end? Should equal 1. This last column should come out to a 1. Okay, and this is sine squared plus cosine squared, it should equal 1. Now, when you see sine squared theta, that's the same thing as sine of theta in parentheses squared. Those two are equivalent to each other. So I'm just going to write that above here so you can see it in both formats. Okay, if you need to write that off to the side, you can. Sine of theta in parentheses squared is the same thing as sine squared of theta. It is the trig value that's being squared. It's not theta that's being squared. Y'all understand that? If you need to make a note that this does not equal sine of theta squared, that is not the same thing. Okay? That's squaring the angle before taking the sine value. That's not what we're doing. We're taking the sine value and then squaring that. Okay, so make sure that's clear. All right, at 45 degrees, if you need to sketch a picture, sketch a picture. 45 degrees. What's the ordered pair at 45 degrees on the unit circle? X and Y are both positive, square root of 2 over 2. Okay, so that's, remember, cosine is the X, sine is the Y. So sine is square root of 2 over 2. And then we are squaring that, right? When you square a fraction, you square both the numerator and the denominator. So when I square this numerator, what happens when I square square root? Yeah, I'm just left with what was underneath, which is the 2, right? What happens when I square 2? Does 2/4 reduce? All right, so I get 1/2 here. Okay, now I'm going to do cosine. Well, cosine's the exact same thing here. So that's also going to come out to 1/2. What is 1/2 plus 1/2? So that one checks out, right? It does equal 1. Okay, we're going to check 135 now. 135, that's the 45-degree reference angle in quadrant 2. So it's a very similar ordered pair, except this time your x, your cosine, is negative. Take your test. Okay, you can sit anywhere there's an empty seat. I'll bring you your stuff. Okay, so y'all go ahead and try that one. Take a second. You're doing the same process. Be aware, pay attention that that negative is part of what's being squared. So when you square a negative, what happens? It comes out positive. Okay, so go ahead and do that one. You see it in where? All right, so hopefully you did this and it came out the same. The sign was still positive, so it was exactly, I'm just going to put the quote things there to repeat the above line. You get the exact same thing. Okay, when we do it for cosine, it's slightly different just because there's a negative, but when you square the negative, it comes out positive, so it still comes out to 1/2. So we again have 1/2 plus 1/2, which still equals 1. Okay, if we did every 45-degree reference angle, it would be 1/2, 1/2 equals 1. Okay, so luckily somebody angle. If I go to 220, That's only 30 degrees. Oh, hang on. We have 180. Let's do our 30-degree reference angle here. What would it be? 210. Okay, 220 is not one that y'all have memorized. 225 is the 45 reference. And then 240 is your 60-degree reference. Okay, but let's do 210 so that it's one from the unit circle. If we did 220, we would just have to do that in the calculator because it's not one that we have memorized. So let's do 210, which is a 30-degree reference angle. At our 30-degree reference angle, cosine is √3/2. Sine is 1/2. But we're in quadrant 3, so what do I know about both of those? Both negative. So for sine is the y, it's 1/2, negative 1/2. So when I square that, the negative becomes positive, and we said if we square a fraction, we square the top and the bottom. So 1 squared is still 1, and 2 squared is 4. So that comes out to 1/4. Okay, cosine, I've got negative √3/2 squared. So again, if I square this negative, it's going to come out positive. If I square the square root, it cancels and I'm left with just the 3. And when I square the 2 in the denominator, I get 4. So I get 1/4 and 3/4. What's 1/4 plus 3/4? That's also 1. That one checks out. Okay, and then last but not least, okay, 330. You know what? That's another 30-degree reference angle. It's going to come out the same. I didn't draw that very good, but it's also a 30-degree. So it's going to be √3/2 and then negative 1/2. So it's the same values. It just switches which one was negative, which won't matter because we're going to still end up with 1/4 and 3/4, which the sum is still 1, right? Y'all see that? Okay, so we will pick up there tomorrow. So we've come up with our first Pythagorean identity.